Let's journey to the center of the Earth to discover what lies beneath. Giant mushrooms light up an underground sea while ichthyosaurs glide past a lost world hidden beneath our feet. Sounds pretty epic, right? That's the kind of fantastical adventure Jules Verne cooked up in his classic novel, Journey to the Center of the Earth. Whoops, reality shows a glowing cross-section of the real planet Earth. Because sorry, Jules Verne, as much as we love the idea, there are no subterranean forests or prehistoric beasts roaming around down there. What we actually find is something arguably even more mind-blowing. A 6,000-degree metallic heart, spinning faster than your car engine, all wrapped up in rock that flows like super thick peanut butter, but over millions of years. In the next few minutes, we're going to drop straight through the Earth's crust, mantle, outer core, and deep into that mysterious inner sphere. We'll be comparing Verne's incredible 1864 dream with the stranger-than-fiction truth that modern science has uncovered. Ready to trade those glowing mushrooms for molten iron and a truly epic journey of discovery? Let's go. First up, we hit the Earth's crust, which is basically the shell of a hard-boiled egg, ridiculously thin in comparison to the rest of the planet. Think about it. This is the part we live on, the solid ground beneath our feet, and it's surprisingly delicate. Beneath the vast oceans, it's only about 5 kilometers thick, barely a scratch on the surface. But under the towering continents, it can push towards 70 kilometers deep, forming mountain roots and stable land masses. Humanity's deepest scratch into this shell? That would be the Kola super deep borehole in Russia. After decades of drilling, they managed to reach just over 12 kilometers down. And what did they find? Not Verne's passageways, but temperatures soaring past 180 degrees Celsius, which is equal to 356 degrees Fahrenheit. Hot enough to bake bread, melt solder, and absolutely wreck even the toughest drill bits. Verne's heroes, Professor Leidenbrock and his nephew Axel, famously started their journey in Iceland's Snæfellsjökull volcano. They believed magma tubes would give them a convenient elevator straight to the core. A nice poetic idea for a novel, but most volcanic conduits actually dead-end into solid rock within a few dozen kilometers. They're not express lanes to the planet's heart. Still, even if it doesn't hold ancient oceans, the crust does hide some real surprises. Scientists have found microbes, affectionately nicknamed deep life, living in boiling darkness 2 kilometers down. These tenacious single-celled organisms munch on minerals, surviving in conditions that would instantly kill most other life. They're older than the dinosaurs, and frankly, they have zero interest in chasing explorers. No dinosaurs themselves, just microscopic life thriving in the extreme. Past that thin crust, we plunge into the mantle, a colossal layer extending nearly 2,900 kilometers deep. It's made of dense silicate rocks, and it's nothing like a lava lamp, despite what you might imagine. While it's solid, the mantle behaves like an incredibly viscous fluid over geological timescales. Think of it more like crazy thick honey, slowly convecting and churning over millions of years. Here, the pressures jump to an astonishing 24,000 atmospheres, and temperatures climb past 900 degrees Celsius, which equals 1652 degrees Fahrenheit. Under these conditions, the minerals within the mantle actually rearrange their crystal structures. For instance, olivine, a common green mineral, transforms into spinel. This process releases subtle flashes of heat and energy, which are crucial. These slow, powerful movements are what ultimately drive plate tectonics, constantly reshaping our planet's surface. Verne, in his boundless imagination, wrote about a vast cavern in the mantle, 50 kilometers high, lit by electrified gas and home to a subterranean ocean. It's a breathtaking image, but let's do a quick reality check. Open pockets that big simply can't exist at these depths. The immense pressure from the overlying rock would slam the roof shut faster than you can say geodynamics. However, tiny pores do hold water, not flowing freely, but locked away inside specific minerals like ringwoodite crystals. Researchers estimate that this hidden reservoir of water, trapped within the mantle, could equal the volume of 3 global oceans. It's a staggering amount, but definitely not in a swimmable cavernous form. You won't be taking a dip down there anytime soon. Next, we enter the aptly named transition zone, spanning depths between 410 and 1660 kilometers. This isn't just another arbitrary boundary. It's a place where things get really interesting and really dramatic. It's a zone so abrupt that even earthquakes change speed when their waves cross it, acting like a seismic speed bump. Here, enormous slabs of ocean floor dragged down by tectonic forces pile up like rugs in a hallway, sometimes stalling for millions of years before sinking further. Temperatures here continue to soar, pushing beyond 1,600 degrees Celsius or 2,912 degrees Fahrenheit. But what's truly dazzling about the transition zone? Diamonds. These precious gems crystallize under these exact conditions of extreme heat and pressure. They then hitchhike upward in volcanic pipes, called kimberlites, to eventually sparkle on engagement rings and adorn royal crowns. Verne, surprisingly, never mentioned diamonds in his subterranean journey. He did, however, imagine a storm-tossed sea at similar depths, complete with ancient marine life. The truth is, to survive down here, you'd need a truly super-heroic diamond submarine. Why? Because steel, even the strongest alloys, would turn to taffy under the colossal load of pressure and heat at these depths. It's a testament to the Earth's raw power. Plunging even deeper, we enter the lower mantle, a vast region where pressures exceed 1,000,000 atmospheres. Here, the rock remains stubbornly solid despite temperatures reaching an incredible 3,700 degrees Celsius or 6,692 Fahrenheit. How is that possible? It's all about the pressure. The atoms are squeezed into ultra-dense, tightly packed structures, preventing them from melting into a liquid state. This is where the planet's immense convection engine truly hums. These slow, powerful currents within the lower mantle are the ultimate puppet masters, shuffling the tectonic plates above, driving the very volcanoes that fascinated Verne, and triggering the earthquakes that shape our world. The lower mantle is also home to some truly colossal and mysterious features. Scientists have identified giant blobs of hot, dense material that they literally call LLSVPs, large, low shear velocity provinces. These massive structures, some the size of continents, are thought to be anchors for volcanic hotspots like Hawaii and Iceland, steadily feeding magma upwards for millions of years. So, while Verne picked the right volcano in Iceland for his adventurers, he definitely got the elevator shaft wrong. To descend further into the Earth's interior, you'd have to drop another 2,000 kilometers through progressively denser and hotter rock until, finally, the liquid outer core makes its appearance. At an astonishing depth of 2,900 kilometers, we hit the outer core. Imagine a swirling, churning ocean of molten iron and nickel alloy, stretching for thousands of kilometers. Temperatures here hover between 4,000 and 6,000 degrees Celsius, or 7,232 and 10,832 Fahrenheit, rivaling the surface of the sun. Yet, despite this intense heat, the metal stays liquid thanks to the immense pressure that prevents it from vaporizing. It's a dynamic, turbulent place. The flowing currents within this liquid metal act like a colossal, self-sustaining dynamo, generating Earth's magnetic field. This isn't just some abstract scientific concept. This magnetic field is absolutely vital for life on our planet. Without it, cosmic radiation from space would fry life on the surface, stripping away our atmosphere, and the breathtaking auroras we see in the night sky would vanish entirely. Verne's explorers, while measuring increasing heat, never could have guessed that a powerful magnetic field was being born around them. Lose that field, and compasses would spin uselessly. Animals that rely on magnetoreception for navigation, like migrating birds, sea turtles, and even certain bacteria, would be hopelessly lost. It's a silent, invisible shield that protects us every single day. Finally, 5,100 kilometers down, we reach the Earth's enigmatic inner core. Here, the pressure is so colossal and mind-boggling 3.6 million atmospheres that atoms of iron and nickel are forced to lock into a solid metallic lattice. This happens despite temperatures at the sun's surface, around 6,000 degrees Celsius, or 10,832 Fahrenheit. Think about that for a moment. It's hotter than the surface of the sun, yet it's solid. The inner core is essentially one giant, rotating iron crystal, a solid sphere the size of the moon, growing by about 0.5 millimeter each year as liquid iron from the outer core crystallizes onto its surface. It even rotates slightly faster than the rest of Earth, a subtle but significant difference. Verne imagined a glowing void at the very center, filled with a primitive atmosphere, where his explorers might find a new world. Reality offers no cavern, just unforgiving, extreme solidity. Drop a pebble here, and under that unimaginable pressure, it would literally weigh a ton. So how do we know all this without ever having sent a probe down there? The core's discovery came not by digging, but by analyzing seismic waves from earthquakes. Essentially, every major earthquake gives the planet a giant ultrasound, allowing scientists to map its hidden internal structure. It's a fair question. No one has ever sampled the Earth's core, so how certain is science about all this? When earthquakes rumble, they send two primary types of waves zipping through the Earth's interior, carrying crucial information. P waves, or compressional waves, squeeze and expand rock like sound travels through air, and they can pass through both solids and liquids. S waves, or shear waves, move rock sideways, like shaking a rope, and critically, they travel through liquids. When these S waves hit the liquid outer core, they simply disappear. The P waves, on the other hand, slow down and bend as they pass through the molten outer core, and then speed up again in the solid inner core. By meticulously studying the travel times and paths of these seismic waves from thousands of earthquakes, seismologists can map the boundaries between the different layers with incredible precision, often down to within a few kilometers. It's an ingenious method that turns every quake into a free, albeit indirect, probe of our planet's hidden depths. Verne's characters decoded a cryptic 16th-century runic manuscript to find their way. Modern geologists, in contrast, decode planet-shaking vibrations. It might be less romantic than ancient runes, but it's infinitely more accurate and revelatory. Despite all the fantastical elements and scientific inaccuracies, Verne absolutely nailed one crucial thing. The Earth is layered and dynamic. His novel, published in 1864, ignited public fascination with deep time and deep space, inspiring generations of readers and scientists alike. It truly paved the way for science fiction as a genre, showing how thrilling the unknown could be. Consider this. In 1864, the idea of continental drift, where land masses move across the globe, was utterly unthinkable, considered pure madness. Yet today, plate tectonics is fundamental textbook science. Verne's incredible imagination, even if his details were wrong, primed readers to accept a moving, evolving planet long before GPS could even measure plate motion at the leisurely rate your fingernails grow. He made the impossible seem possible, making the eventual scientific discoveries feel less alien and more like a continuation of a grand adventure. If this layered journey through our planet's fiery heart has fried your mental circuits in the best possible way, then hit subscribe for more reality checks on classic tales and explorations of incredible science. And seriously, drop a comment below. What part of the real Earth blows your mind more? The ultra-hot flowing rock of the mantle, or the solid crystal heart of iron spinning inside our world? We'd love to hear your thoughts. We started our journey with glowing mushrooms and prehistoric beasts, and we've ended with a metallic, superheated crystal core. The truth might lack Verne's dinosaurs, but it teems with physics wilder than any fiction. Rock that flows like treacle, iron that stays solid at sun-like temperatures, and a magnetic shield stitched together from swirling liquid metal. Jules Verne took readers on an unforgettable adventure through his imagination. But science, with its relentless curiosity and ingenious methods, takes us even further, revealing a planet that is truly alive beneath our shoes. Next time you feel the solid ground, remember, you're standing atop a 6,000-kilometer stack of mystery and wonder, and the only drill you truly need to reach its depths is your own insatiable curiosity.